I'd like to welcome everybody to the start of the workshop proper after the 1.5 days in school. And our first speaker to get us started on this is Peter Wadley from Nottingham University.
Thank you very much. Good afternoon, everyone. I'd like to thank the organisers for putting together such an exciting workshop. It's my first experience of a dedicated antiferromagnetic spintronics workshop. I'm going to talk today about current-induced switching of an antiferromagnet. I realise that for such a specific workshop I could perhaps have been more specific with the title. So I'm really looking at current-induced torques and switching of copper manganese arsenide. It's a big and growing collaboration between a number of the key institutes. The University of Mainz is listed here. We have people from Diamond also here. People from almost all of these institutes here and actively participating. So what I'm going to talk about is just a few minutes on the motivation. I probably don't need to convince everyone here that antiferromagnets are interesting, but I'll just dwell on the key points and how we can use them for spintronic applications. A very brief introduction to the system which all these results will be on, and then move on to the current-induced switching of the spin axis in this system, and then imaging of this domain structure and also of the switching itself. So the motivation is growing all the time as well, but not only there's a huge range of systems, ranging from oxides all the way to metals, and also some topologically interesting systems which are going to be discussed later in the workshop. Some of the spin orbit-based magnetotransport effects that have been used and are used in ferromagnets are equally present in antiferromagnetic systems. They were predicted, and a lot of them have also now been demonstrated. Antiferromagnetic systems don't have stray fringing fields, so you can pack them closer together potentially, and they're insensitive to external applied magnetic fields. We have ultra-fast dynamics, a lot of this notably demonstrated by Thiel Larsen's group a lot earlier, and also more recent predictions of ultra-fast domain motion and coherent rotation. And then, topologically, some quite interesting systems, and I'd like to point out this switchable, magnetically switchable Dirac semimetals, which Libor Schreikal will talk about on Thursday morning. And also things like antiferromagnetic skermionic compounds and non-chiral systems, non-collinear systems. So, spintronics with antiferromagnets. As Lewis Nail pointed out, we've seen this slide a few times, they're interesting but without application. We know that they have some applications as a kind of auxiliary role in hard disk read heads and things like this for pinning ferromagnetic layers. But he also interestingly noted in exactly the same lecture that effects that are an even function of magnetization are of course present in antiferromagnetic systems. An example of that is the magnetic anisotropy energy, so the magnetocrystalline energy, equally present if you rotate the direction of the magnetization of a ferromagnet with respect to the crystalline axes, you change the density of states. That's also the case in an antiferromagnetic system. So to make them more widely applicable, we need the ability to efficiently control and read the spin state. So talking about reading the spin state first, the simplest way of reading the spin state in a ferromagnet, which is equally applicable in an antiferromagnet, is simply anisotropic magnetoresistance, an effect that's been known about for a long time. So here the resistance state changes dependent on the current direction with respect to the magnetization direction. And one can imagine making a simple, or it has been done, making simple ferromagnetic bits where these are the information storage. And you can do the same nominally with an antiferromagnet. So another a consequence of this anisotropic magnetoresistance is the planar, the transverse component of this. If you rotate the resistivity tensor, you simply end up with a component here because of the tilting of the equipotential lines. So whereas the straightforward longitudinal resistance has a cos2 theta dependence, the transverse has a sin2 theta dependence. And the reason that I'm pointing that out is, in this case, you have the two high states at 45 degrees to the current path, and it's it's a nice way of measuring your magnetic state. It's less sensitive to extraneous effects. So it's something we'll make use of. So moving on to controlling the antiferromagnetic order, you've seen this picture before, probably from Frank Feynman. One needs to generate an alternating effective local field that has a subunit cell resolution and that correlates with your spin sublattices. That seemed, to me at least, like almost an impossible task, but this paper here by Jakob and Tomáš's group showed that in certain symmetry systems, this could be achieved by running a ferrite through them. And it's an analog of the inverse spin galvanic effect, whereby in a non-centrosymmetric system, like a zinc-blende gallium arsenide, if one applies an electric field, you redistribute spins on the Fermi surface, and you end up with a non-equilibrium spin distribution. And this leads to a global spin polarization. And this was utilized very nicely by Chernyshov et al. To switch to magnetization in a ferromagnet. Now this is not useful for us, particularly in the case of an antiferromagnet, because this global field will struggle to rotate the spins in different directions. And of course they're very strongly exchange coupled. But what was, I think, ingeniously suggested by Jakob and Tomáš, also in the static case by Zhang et al., is that if one considers the local symmetry within the unit cell, you can find local inversion asymmetric points. And this is the case, for instance, in a compound like silicon, which has normally this diamond structure. But points like this are inversion asymmetric locally. And what you end up generating if you run a current through them is essentially a texture in the spin polarization. And if one is able to get that to correspond with the spin sublattices, it ties them very strongly. So this paper ended up, this PRL paper, by suggesting a device like this geometry where you really have simply a cross. In this case of manganese 2 gold, and one is able to run a current first in one direction and rotate the spin axis coherently perpendicular to the current, and then in the opposite direction. So after discussions with Jakob, it became clear that copper manganese arsenide had a similar point symmetry and should indeed work as well. So we decided to look for this. So I'll just briefly step back to show you one slide on this system. Copper manganese arsenide is a tetragonal collinear antiferromagnet. I'm not going to say very much about this at all because Richard's going to talk in detail about the growth and structure of the system. It's enough to know that it's a high temperature antiferromagnet with a very simple collinear spin structure. So the devices we actually chose to look at this make use of this AMR symmetry, which we just discussed a second ago. So you have, the basis of it is this cross, where you run the current in one direction and then you run it in the orthogonal direction. But in this case, the reading is done by a small measuring current at 45 degrees to this, so that we're reading the maximum in the planar hall. And this slide is not very pretty, and it's probably one that you haven't seen, but it's the very first data taken in December 2014 on this system. And although it's messy, these red points are pulsing in one of the directions and then the black in the orthogonal, we already can see that there is something happening there. Through a little bit of improvement, we came to this. So this is data taken by CuMnAs and Vivian Schuler in Prague. And this is the data that finally made it into the science paper. And here we have several pulses in the same direction, back again. And one can see just how stable these states are. In fact, even the individual states. And this was done on this type of device geometry, so optical photograph microscopy. And we're switching currents that are comparable to ferromagnetic STT-MRAM devices currently used, all done at room temperature. And one can, for completeness sake, check all of the symmetries that should be there. So in the transverse component here, we have the minimum and maximum of 45 degrees to the spin, and nothing in the orthogonal and parallel, and the corresponding in the longitudinal that we expect. So it has the correct symmetry at AMR. So this brings us into a position where in ferromagnets you can use this global inversion symmetry to manipulate the magnetic order, but now this local inversion asymmetry in antiferromagnets can do the same thing for you. When we looked at, well, you can see this almost straight away, but if you look in a bit more detail at the dependence on the amplitude of the current you're using to switch this, or the time, you can see that there really is not, it doesn't look like a coherent single switch, right? It's domain-like, and it tends to saturate. I'm not going to talk about this in any detail, but I'd encourage you to go and see the talk by Jörg Wunderlich, who's going to present some of the ways in Prague that they've utilized this in an absolutely beautiful, reproducible fashion as a multi-level memory cell. And also, Xavi Marti's talk on Thursday, I think, will talk a little bit about how to use this in your application sense. So that paper is also on archive. But we would like to see independent evidence of the magnetic switching, and this was not in small part motivated by the referee's desire to also see this. And one of the ways to do this, so this is essentially part 2 of the talk, is to look at this with a technique called X-ray photoelectron emission microscopy. What we do here is we take it to a synchrotron facility, and you use linearly polarized light to probe a particular transition. In this case, we're looking at the manganese 2p to 3d transition. And I won't go into the details of this, but one can see that if you look at the difference between the absorption with the two orthogonal polarizations, one can use the peak and trough of these differences to image the surface. And in this case, I'm trying to show just 2 different domains. They will have different contrasts. So this is the actual device and a magnetic contrast image taken from the beam. And in this case, we're using slightly different geometry than was used in the previous experiments because of the limited number of contacts in the beam. Here we have a cross, and we achieve the orthogonal pulses by pulsing down 2 arms at once, and then the other 2 arms from the side, and this generates a net vector in the center which has the same effect. What's nice about this is you can also measure the largest and easiest signal electrically in parallel. So this is the measurement of the transverse AMR. And what I'm going to show you now is a sequence of 16 switches that we've seen in the transport before, but this is now simultaneous transport and beam imaging. So we're going to start here, and the black and white contrast is really ultimately the vertical and horizontal alignment of the strings. You have to watch quite carefully. Up here in the corner is the switching from the electrical signal measured in parallel. And what we're looking for is a light, dark pattern. I don't know how well this comes out on the screen, though. It never overwhelms people the first time I showed them this. But for me seeing it the first time, it was overwhelming. And I think with a little bit more analysis, I can convince you that this is really something magnetic happening in a reproducible fashion. So firstly, I'm going to concentrate just on 2 regions. They're not picked for any particular reason other than the fact that you can see them switching, but they're extremely common. So here we have the alternate pulses, and I think that you can see this large black area up the top here turning on and off as the pulses go. Here we have, you can go mad staring at these images, so you start to see all kinds of things of the day. So here I see a poodle. Appearing, disappearing, appearing, disappearing, appearing, disappearing, appearing. And if one looks at this a bit more statistically, you can sum the entire image. This is a difference image here. It should look red. If this was coherent switching, it would look red, showing the direction that it's switching to. But what's interesting is there's really a range of different levels of switching, and even you see some anti-switching areas that are switching in the opposite direction to that predicted. They're a minority, but they do exist. But what was extremely pleasing is if you sum over the entire image and compare it in parallel to the electrical signal, you really see the switching in both. And that's fantastic. There's no real correction or anything needed to that. You see the switching. If we take these 16 back and forth images and we statistically analyze the 2 sets up and down, one can see, so this is just a histogram of the distribution of intensities, one can see where these large differences are happening. One can also correlate this difference to the applied current, and it correlates perfectly. And this is an important step because beam is extremely surface sensitive, so we're really looking at the top 3 to 5 nanometers as the majority of our signal. But it's nice to know that this bulk electrical measurement is really correlated with what we're seeing in the beam. In fact, you can see that over this range, the size of the XMLD signal is linearly correlated with the size of the electrical signal. And if one extrapolates that, it does have large error bars because it's quite a long extrapolation, to the case of the maximum XMLD switching, you can estimate that the size of the AMR predicted for a coherent switch of the entire system will be about 3%, which is pleasingly large, but not unreasonably large. Back one slide. So this all seems like a really nice, coherent picture. It's not quite what we wanted to see in the sense that this domain structure is extremely complex, but it does seem to correlate very well with the transport. But more recently, we've looked at the domain structures, and there is a wide range of domain structures, so there's still a lot to understand about this. And I'm just going to show a couple of these different domain structures in the same compound, but grown on different substrates and in slightly different growth conditions. On the left here is the one where we have all the switching data, and it was the layer used for the science paper as well. On the right here is another layer that you will see a lot more of the data from in Jorg's talk. Switches beautifully as well, but the domain structure is really, really different. On the left here, you'll have to take my word for it a little bit, but this looks to us easy planar, meaning you can rotate the sample at almost any angle, and you see almost the same amount of domains. So our interpretation, at least mine is, I think, at the moment, is that the anisotropy is so weak that the spins really don't seem to mind very much where they point. In this layer here, which is slightly thinner and grown on gallium phosphide, it's really quite strongly biaxial from the domain structure. You see almost nothing at 45 degrees, so it's very weak contrast. And in this case, the domain size is really much larger. So here, it's of the order of microns and above. Here, typically, it's we think about 70 nanometers or something like that. On the far right is a thinner layer yet. And this is almost entirely uniaxial, apart from these dark lines, which are actually 180-degree domain walls. So they separate AB lattice swapped domains, or 180-degree domains. And if you look at that on a larger 40-micron field of view, you see some really nice, interesting domain patterns. And I'm showing this because one of the things that has come out recently in Helen and Hyder and Tomasz's paper is the prediction of just how fast these domains domain walls should move under the influence of a nail-roll spin orbit torque. And that's something we're planning to take a bit of a look at in December and preliminary look at on the synchrotron. The width of these domain walls, best estimate, is somewhere around 200 nanometers. It's a little bit hard to say for sure. What I'd like to do now is I'm not going to discuss this in any detail, but I'd like to point you to a couple of these are important discoveries, I think, in this field. So I talked about ultra-fast, the dynamics of the system, but of course, in order to fully realize that, you need to be able to both write the state fast and read the state. And this is an example here of work done by Vít Seidel and Peter Němec. Vít, I believe, has a poster session on Thursday. And this is an optical pump probe technique for determining the nail vector of the system. So they are able, in the laboratory, to determine which direction the nail vector is pointing in. I'm not going to go into that in detail, but please go and see Vít's poster and discuss it with him. These are the latest results from work done by Kamil Olnik in combination with ETH. And Chablis and Vivian. And what we're seeing here is the size of the signal from switching induced by 250 picosecond pulses, which I think is a phenomenal result. They're able to see small differences from pulses of that kind of width. And another thing that has been done is putting these devices on the USB chip, and I'd encourage you to go and see Charlie's talk for more information on that. So, the outlook, I think, is really good for this, this system. So a couple of things to say. I think we have an incredible tool to study the domain behavior and dynamics of antiferromagnets, and plenty of ideas of what to do with that. As I said just now, switching has already been achieved with 250 picoseconds on essentially, I think essentially unoptimized devices. I mean, really the same kind of device geometries I was going to show, just a little bit smaller. Multi-level memory cell ability or property has been demonstrated in these devices, and that's something you can see even here from this. This is the same data, I believe, that is in the science paper. You can see 3 distinct states, but they have now in Prague achieved something like hundreds of different states. So picosecond switching is expected, coherent reorientation in domain motion. We have a way to optically read the nail vector, which is an important step. And we can demonstrate things like insensitivity to external magnetic fields. And with that, we're going to end here with plenty of time for questions.
Thank you, Peter. Questions?
On the slide where you've shown the switch in anti-parallel, is the size of U coincide with the size of the sample? I mean, these blue points which you showed, are they at the border of the sample or are they at the border of the here?
These?
Yeah. Is
No,
this at the border of the sample?
No, they just occur at various different points. You can actually see more of them. Here they are on the border, but there's one here. You can see them quite regularly.
Can you see any difference if you change not the direction by 90 degrees, but if you change just the polarity?
It's something we try to look at. Of course, these experiments, they take quite a long time. So normally, so far, we haven't had time to explore that in any kind of detail. But superficially, I couldn't see any particular pattern to it. But we haven't done enough measurements to rule that out. And I think it's something well worth looking at.
We're close to time for no more questions.
Too quickly.
Can you show this slide where you have these different thicknesses of things? So, what is the difference between the central and the right one? I mean, from the point of view of production of the sample, except the thickness. Are they exactly equivalent, the 60 and
No, that's the problem. I mean, the reason I don't want to draw any broad conclusions from them is every one of these layers so far has been grown for a specific reason. And that means that it's not, things were done differently. So in this case, this one had quite a large buffer layer for historical reasons. I don't know what difference that would have had, but also this layer was grown a little bit later and we had more accurate temperature control of the substrate. So I can't, although there is really a clear difference between them all, I can't really associate it with something we're doing. I think it really requires a systematic study of the growth condition. It's something we really want to master because this sample is extremely interesting to me now.
Any more questions? I guess it was a very complete and comprehensive presentation. Thank you very much.
Thank you.